Okay, my name is Chris Johnston. I'm a researcher here at AFBI, and my colleague John McIlroy, who'll talk to you after me. I think you may have left that last stand or one of the stands earlier with a message that we've got this phosphorus surplus on our farms of about 11 kilos per hectare per year. It has been more, and it may well increase, but it's too high, and we kind of have a feeling that phosphorus surplus needs to come down. Farming phosphorus, I guess, is one of the causes of water quality, which we need to manage. I want to tell you here now about a feasibility study we've been working with the Department of Agriculture on through the Small Business Research Initiative, and where we're trying to reduce that phosphorus loading on farms. And the strategy, just in a nutshell, is as follows. Really what we are trying to do is target farms with high intensive farms with a high P index, farms with a surplus of phosphorus. We want to direct that nutrient on farm, that slurry, through nutrient management technologies like screw presses. On farm screw presses are centrifuges. Those technologies are actually running here. You can see them, screw press anyway. But also the addition of another technology which we are starting to see in the continent a bit more, and we'll probably see that here in Northern Ireland, which is a mobile screw press. A screw press that can go onto farm and separate a lot of slurry, creating a solid product. Now that solid product contains a significant amount of the phosphorus. It could be between 20 and 40% of the phosphorus that's within that slurry. That product is also a biomethane feedstock for anaerobic digestion. So the strategy then, or the idea, really, the feasibility, is to move that nutrient off towards an anaerobic digester, where the AD plant now can use that feedstock to produce biomethane. We have a requirement for biomethane. The Committee of Climate Change says we need to get about 3.5 terawatt hours. We do need biomethane in our gas grid if we want that energy independence that we're aware of. So that would kind of make sense. But from a nutrient perspective, where we are really quite interested in is that it'll challenge the excess phosphorus all the way down through into the digestate, where we can then valorize. Valorize, the word we all use just to create value. That digestate out the back of that AD plant, we have technologies that can start to implement a value into that, so that phosphorus can become a phosphorus fertilizer or blended fertilizer. The nitrogen extracted can be a nitrogen fertilizer. Even other carbon products can be created. We hear about biochar from time to time as well. But bringing all that nutrient down through the whole process, using AD plants as a biorefinery to manage that nutrient off farms through this process is where we're sort of aiming for. So before I pass over to John, just to summarize, this kind of idea, this feasibility plan that we're working through with DAERA, and we'll hear more about it in coming months, would develop low carbon bioenergy, low carbon methane on a gas grid, decarbonising Northern Ireland. It'll valorize the nitrogen, phosphorus, and even the biogenic carbon dioxide is a valuable product that we need. We'd have less reliance on fossil fuels. We'd have a lower carbon footprint. We'd reduce that on-farm P balance, which is really why we're talking about this. Protect water quality as a result. And of course, we have to align with the Northern Ireland net zero goals by 2050. It's a legally binding act. So we've all got a role to play there. And we've got an opportunity of seriously creating green jobs, real green jobs in sectors that previously did not exist through all the different steps I was mentioning there. Key messages, however, okay, phosphorus runoff does cause 60% of our water quality pollution at the moment from agriculture. Removing phosphorus from farms can reduce the land spreading pressure of that nutrient. We bring those nutrients down. We need, however, to evaluate the cost models of these interventions, and that's the point of these feasibility studies that we're conducting with DAERA. Is we need to evaluate it. We need to make sure that this kind of thing could actually work, is economically feasible and practical. And we need, of course, to have the acceptance of new technologies, and we need societal acceptance as well that this whole thing could actually work, and the agricultural community would accept it. Finally, of course, we do need to ensure that we are managing biosecurity, methane emissions on farm slurries, and of course ammonia is a big one as well. Ammonia has to be managed. We can't just solve one thing while creating another problem. And on the ammonia point, I'm going to hand over to my colleague John McIlroy.
Thanks very much, Chris, for the introduction. So as Chris was saying, my name's John McIlroy. Chris has already touched on the need for better management of nutrients on farm, and that's really crucial. It's about closing the nutrient loop on farm, about maximising the nutrients we already have on the farm, trying to reduce the reliance on imports onto the farm. And one of the most valuable forms of nutrients on the farm is nitrogen, and one of the largest loft pathways for nitrogen on the farm is through ammonia emission as a gas. So ammonia, as well as being a form of nitrogen which is lost to the atmosphere, meaning that nitrogen is no longer, used agronomically, the emission of ammonia is also has environmental repercussions and has environmental impacts, particularly for designated sites. So currently, it's a major challenge for Northern Ireland agriculture. DAERA have funded AFBI to carry out a large programme of work in this area, which we've been doing over the last number of years. And today, I want to present some of the findings from some of that research that we carried out. So it's effectively what we did was we used the UK National Ammonia Inventory Model to model a series of dairy scenarios, so typical practice dairy scenarios across Northern Ireland, and then apply a series of ammonia mitigation strategies to those baseline scenarios to see by how much we could reduce ammonia emissions on typical Northern Irish dairy farms. So we effectively started with two typical practice systems. We modelled a fully confined system and also a more traditional grazing housing system. The grazing housing system was set at 186 days per annum grazing. In terms of the housing systems and the slurry management systems, both of these systems were the same. So they were effectively both naturally ventilated, slatted systems where part of the slurry is stored under the house, another part of the slurry is stored in an outdoor store. Then that slurry is spread in the field using a splash plate. We also modelled the fully confined system as having higher milk yields, reflecting the typically higher milk yields of those systems. So then what we did was we took a suite of 6 ammonia reduction strategies which would be applicable within a dairy context within the dairy sector, and applied those 6 strategies to these 2 different systems. So the 6 strategies we looked at were reducing the dietary crude protein of the herd from 18% to 16%, extended grazing, so adding 2 weeks onto the grazing period, and that could be a week at either shoulder of the season. We also increased the scraping frequency within the house to scraping the floors and scraping the passageways every 2 hours, which is seen as the optimum scraping frequency to reduce ammonia. We added a cover to our slurry store, so we covered our outdoor slurry store. We also moved away from spreading our slurry by splash plate and moved to a trailing shoe method for this modelling, but it could be another low emission spreading method such as a dribble bar or even a shallow injector. And then we also moved away from the application of straight urea and used stabilised urea or protected urea instead. So what we found was that when we applied these 6 ammonia reduction strategies to these 2 baseline scenarios, we achieved a 43% reduction in ammonia emission across both scenarios. Now, we did note when we did this modelling that the fully confined system actually produces 57% more ammonia per cow than the grazing housing system, and that's because a fully confined system produces a lot more slurry. There's a lot more excreta deposited in the house, urine and faeces mixes. That has to be stored, it has to be mixed, it has to be land spread, and that generates ammonia emissions. However, because of the higher milk yield of the fully confined system, what we actually found was that the ammonia emission per litre of milk was actually reduced to 33% for the fully confined system. Now, as I've mentioned, whenever we lose ammonia gas from our agricultural systems, what we're actually losing is a valuable form of nitrogen, which we then often have to import through inorganic fertilisers. So what we actually determined was that in terms of the nitrogen saved in these systems and the extra nitrogen that we would have in our slurry when we apply, there was actually a nitrogen saving of about £461 and £963 respectively per annum for an 100 cow herd based on a nitrogen cost of £1 per kilo of nitrogen. So significant cost savings across both scenarios. What we did more recently was we actually took, we wanted to look at some of the more novel bespoke housing systems that have become available and have started to be used commercially in countries such as Germany, Holland and Denmark. So we modelled an in-house slurry acidification system, and we actually found that type of a system could reduce total farm ammonia emissions by up to 73%. We also looked at a negative pressure air scrubbing housing system, and that system was modelled as having a total farm ammonia reduction of 70%. Now, it has to be said that these systems have higher capital costs, obviously, as they require a bespoke build often to install these types of systems. Retrofitting these systems generally isn't as efficient, so you would have a reduced efficiency if you try to retrofit these systems to an existing house. So overall, the key takeaways are that significant reductions in ammonia can be achieved on dairy farms using technologies which are applicable and could be applied. And some are changing sort of management strategies. Some would require infrastructure and some investment on the farm, obviously. But that a 43% reduction is achievable potentially on dairy farms. And in terms of the single most effective method, low emission slurry spreading really is a key method within this suite, as the low emission spreading itself could give us anywhere between 30 and 60% reduction in emissions at land spreading. So really that concludes my brief presentation. Both Chris and I are happy now to take any questions for either of the presentations this morning.